Okay, thanks to the organizers for giving me this chance, and thanks for everyone attending. So I'll be talking about global warming, but not the one that will kill us all. I'll talk about some other kind of warming. Instead, you have this. I'll talk about this curious phenomenon, which sort of all of you should be able to relate. So basically, you take a rod like this, except this is a quantum system, so the quantum rod, and you cool one end, a few sides at one end. And what you find is that that end cools down and everything else heats up. So this sort of counterintuitive effect happens. So I'm not creating energy, of course, out of thin air. The world still exists. So what's going on? That's what I'll talk about. Okay. So the setup is basically, as I said, some lattice system, let's say some spin chain, which is coupled to some other sites, which I'll call the bath sites. Except the bath, these sites can be, there can be finite number of sites here which are being actively cooled to their own ground state. And in principle, you can also add some pump, heating as well as cooling to these sites in order to keep this at some sort of set temperature. Right? So that's why I'll call this part the bath and this part the system. And the question is, if I do this kind of process, what happens to the system? And so this was looked at recently in a few papers. In particular, this paper showed that if you have a free fermion bath, and if you model these coolings and heatings by Lindblad, so Markovian dissipators, then the system indeed reaches the bath temperature, which is what you intuitively expect, provided you satisfy these conditions. So the bath is very large with a bandwidth larger than the system, so meaning that any energy gap in the system will be found as some excitation of the bath. The coupling between the system and bath is weak and generic, and also the heating and cooling rates are weak. So that's when the steady state, so this weak means that it will take a long time to reach steady state, but in the steady state, it reaches the temperature of the bath. This you can show, prove, and also there have been some numerical simulations with finite number of bath sites, including by Abhishek and Manas here, who among other things, find that if you have cooling here, not heating, then sympathetic cooling works best, basically in these limits, right? And okay, so what this talk will be about is if you don't satisfy all of these conditions, and under still quite generic conditions, you can have spectacular failure of this, provided you have some symmetries in the coupling that I'll talk about. And in particular, you can get heating by cooling. Okay, so before I go to the this counterintuitive case, let me just put one quick slide on why we generically expect the system to cool down if I have a zero temperature bath, even for a finite bath. Right? So this is, I'm considering a single qubit, a two-level bath here, and some generic system with a bunch of energy levels, and there's some coupling between them which is weak, and the bath, the qubit, is being cooled to its ground state, which I'm calling up, and the excited state is down. And in this particular slide, I will be using some Lindblad description for this cooling. So this is some S plus operator which brings you from down to up state, cooling the bath. And with some rate gamma, which is large compared to epsilon. Right, so if you have such a setup, you can see that there will be transitions between these system energy levels because of the coupling to the bath. System on its own don't transfer between levels, but the coupling is causing transitions that will cause it to reach some steady state. So basically, if you look at the perturbed eigenstates in the presence of this coupling of the whole Hamiltonian, that has some perturbative expansion. So this is the unperturbed state. Then there's some first order correction in the coupling with involving other unperturbed states. Right? So some generic expansion. And then this cooling operator L will cause transitions among these eigenstates of the full Hamiltonian given by the matrix element like that. And that gives you some expression like this. So you don't have to understand all of these steps. This is just to show that you see the denominator here. There's a resonant process by which you can go down from EI to EJ. If that gap equals this delta B of this going up, then this blows up and that will dominate. So that will basically resonantly cool the system. And generically, you see that if EI is greater than EJ, you go down in energy, the denominator is smaller compared to when you go up in energy. So it's clear that this favors cooling over heating. even a single qubit bath. So that's why you generically expect the system to cool down. Right, so now the simplest case where you get heating from cooling. So if I have again, I'm now considering an n-level system, equally spaced, the same setup as before, but now the system bath coupling is given by some spin exchange between the two, between this two-level system and this n-level system. Now you see that although I have, so one thing you notice is that here the energy decreases with the z component, and here it increases with the z component. And so this basically cools both the bath and the system, and this heats both the bath and the system in the coupling Hamiltonian. However, because I'm cooling the bath always to up state, the first term is basically inactive. It cannot apply sigma plus, it's already in S plus. So the only term active is this one, which will heat both of them. And then this will bring it down again, and this will heat up again. So you cannot have downward transitions, that's disallowed because of this SZ total conservation. And instead the system heats up to its highest energy state. And it doesn't actually rely on uniform spacing, it also works for non-uniform spacings. Right? And the same thing goes through even if you have an extended system like this, provided that conserves the total SZ. So if I have an XXZ chain, then again you'll repeatedly increase the SZ through this term here, and eventually you will go to the all up state in the system, which can be anywhere in the spectrum. It can also be the highest energy state. So this is basically saying that if you break the SZ conservation, then eventually go from heating to cooling. Right, so now if I make the bath infinite, so if I can have a XY chain as my bath, and again the similar coupling as before, XY chain is nothing but free fermions hopping, where I have mapped the up state to whole and down state to particle. And then you see that the bath spectrum is then just a tight binding dispersion, which is like this. And then whether it will heat or cool depends on where you are setting the chemical potential of the bath. So if your chemical potential is below here, then all of these are unoccupied. So you only can create particle excitations in the bath. So therefore only the second term is active in the coupling, which pumps SZ into the system. Right? So again, you heat up to maximum SZ. If you have the opposite here, then you only have whole excitation. So the first term is active and it cools to minimum SZ. Whereas if mu is somewhere in the middle, this part cools, this part heats, and you go to some intermediate state. And so if you have an sort of single sort of n-level system now, and if you sweep your mu from down to up, you go from heating to cooling. So this is fitting the temperature, the beta of the system, which is negative here. Yeah, just 1 minute. And positive here. So you see that it's not really symmetric because again the denominator is smaller for the cooling case. If I want to enhance heating, then I can do something. Okay, so this is where I'm hitting resonance. That's where it's resonantly cooling down. If you want to enhance heating, then you can shape the dispersion a bit more like this, where you have fewer K modes contributing to the cooling. And so you have more heating range. So you heat up preferentially. And so one last slide is about whether you can use this effect to produce some kind of mid-spectrum non-classical state where the spectrum itself is not uniform. So if I have some nonlinear cavity where the gap is small here, and this is bigger than the gap, then the system will cool down to this level. And here you'll have a competition of heating and cooling. And so if you vary mu, here you get the most excited state, here you get the ground state, and here you sort of get a shallow peak where the system reaches this 5 level. If you now use this enhanced heating kind of dispersion, then this becomes a lot sharper, and you can sort of produce some n-photon Fock state, which is like a non-classical steady state. Okay, so this brings to the summary. Basically, this is some breakdown of conventional thermalization due to this conserved charge, this SZ conservation, which is related to the energy. In particular, you can get global heating from local cooling, and you can produce sort of non-classical states like that in certain nonlinear cases. Okay, thanks.
Question?
Well, so if you know, if I can, in principle, you can have some setup where you have a spin chain like XXZ chain coupled to an XX chain, and yeah, so I'm actively cooling the thing. So I'm doing continuously, I'm doing work on the thing. Yes, I'm not violating the, yeah. So experimentally, you can design dissipators like this in certain superconducting circuit-like setup, for example, with a few sites here, and you can have lossy sites which effectively dissipates energy from the bath, but you have to do that continuously. So nothing, I mean, no energy conservation is being violated. It's just that you are doing actively, you're cooling the system down. Okay, I mean, yeah, but it's just coming from the SZ conservation. So I mean, it's just, I mean, I've not done, it's just taking this Hamiltonian and solving it, right? So I don't. Yeah, yeah, exactly. No, so here I have Lindblad or some dissipators acting on the bath, which is bringing it down to ground state of the bath. All this is relying on is that SZ is conserved and that is related to the energy. It thermalizes, but not at the temperature of the bath. Yeah, yeah, yeah. But I mean, the setup is slightly different because I'm not really taking, I mean, this bath is different from the conventional bath in the sense that there's really finite number of sites which is being actively cooled. We don't start from the premise, it's just that's what you find. Well, so that's what you find, that it doesn't thermalize with the temperature of the bath. What we just assume is that this is continuously cooled to the ground state. So generic systems will not have this conservation built in. If you violate the SZ conservation, it doesn't work. But if you have some SZ conserving system bath and system bath coupling, and the energy is higher for larger SZ, which you can do by applying some magnetic field, for example, then I don't see any where the arguments break down. If your system bath thing is isolated, then you probably can't. But I'm assuming these dissipators are continuously acting, so I don't know if that breaks the assumption leading to that conclusion. I mean, if I turn off these things, it will not. The temperatures will equilibrate probably, because it will just act as a closed many-body system. What is long enough? Yeah. It cannot be a steady thing for long if you turn off these dissipators. But if you're actively cooling it, then I don't see why that is not allowed. Okay, it is a very surprising finding, but that's what we find. Thanks.
Okay, let us thank our speaker once more.